Our presenter today is Michael Holloway. Michael holds a BS degree in chemistry, a BA in philosophy, and a Master of Science in Engineering. He has 30 years of experience in research and development, technical marketing, equipment reliability and sales, along with publishing numerous books on these subjects. Michael is a certified lubrication specialist, oil monitoring analyst through STLE, a level 1 and 2 machinery lubrication technician, and a machinery lubrication analyst through ICML. Now Michael serves as a principal consultant and certified reliability leader for ALS tribology. Today, Michael will be discussing contamination control. During this presentation, please use your Ask a Question or chat box to ask any questions. All questions will be answered at the end of this presentation. Michael, thank you for taking your time today. Now we'll go ahead and turn it over to you.
Great. Thank you very much. And thank you all for attending our webinar today as well. This should last approximately 50 minutes. We're going to leave a little time at the end for questions if there are any. Today we're going to explore oil cleanliness and particle analysis as it relates to contamination. Okay. So, some reasons to maintain oil cleanliness. Has everything to do with the tolerance between the moving parts. Now, a lubricant's main function is to set up a film to separate those moving parts. Many of the tolerances are quite small, especially in modern engines and even hydraulics and so forth. And microscopic particles can actually get in there and separate up those two surfaces, producing lots of wear. Now, many of these particles are not visible to the naked eye. Several sources of contamination can create a whole host of failures. And one particular source of contamination can be actually incorrect sampling techniques that can lead to some bad sample results. Now on this slide, we can actually see a micron scale and some examples thereof. A human hair typically might be between 75 and maybe 110 microns in cross section. The human eye's visibility limit is down to about 40 microns. Anything smaller, you're going to need a microscope or a magnifying glass to see. To give you an idea of the scale of that, white blood cells are approximately between 20 and 25 microns, and grains and talcum powder are about 10 microns. Red blood cells are about 8, and even bacteria 2. So you can see down the relative size of micronic particles. This has been magnified 800 times, from 25 down to 2. Now, there's lots of different sources of contamination. And contamination could probably be defined as something that doesn't belong in a particular system, and that could create failure. Now, contamination can form in the form of gas, fluids, semi-solids, and solids. Gaseous contamination, such as oxygen or even nitrogen and processed gases, or even refrigerants, can affect the lubricant and can affect the metal surfaces of our lubricated parts. Oxygen obviously produces sludge when the oil or grease starts breaking down, but it can also produce corrosion in metals. With fluid, obviously one of the most common forms of contaminants is water. You're going to find water in the air vapor all the way down to various process. The fuel can be a contaminant in diesel engines and sometimes gasoline engines. Oil can be a contaminant. If an oil is in there for the wrong reasons or because it was top loaded with a different oil, that can become a contaminant as well as processed fluids in a given facility. Semi-solids, such as oxidation resins, which is a production of the oil oxidation, where the macromolecules are starting to assemble into large polymers, forming sludge and varnish and eventually lacquer. Soot being unspent fuel, typically in the form of diesel. Microbial growth can actually be a semi-solid as well and be a contaminant. Various oil additive reactions. Many additives that are found on lubricating fluids are typically polar. They become acidic in nature or alkaline in nature. Well, they're designed to be like that. Well, in the case of certain types of engine oils, we might actually find them to be alkaline in nature, whereas maybe gear oils or hydraulic fluids acidic in nature. Well, if there's a misadd and a different fluid is added into a system, these additives can actually react. And what happens when you add an acid to a base, you create a salt, and that produces a soap-like substance through saponification. That can actually precipitate out as a contaminant and lead to further problems. And delete the whole responsiveness of that additive system. Grease can be a bad contaminant as well. A lot of times when folks are rebuilding equipment, they use grease to help the parts slide in easier. The problem is that that residual grease is left behind and can have a huge effect on the overall functionality of the lubricant. And obviously solid contaminants, rust from the system internally, dirt coming from the outside, metal wear particles, even fibers from filters, slag, perhaps from any kind of maintenance that had been done on that equipment. These all can lead to equipment failure. Give you an idea of some of the tolerances that equipment experiences. In an engine where the rings and cylinders are, we have a 0.3 to 7 micron tolerance. Doesn't leave a whole lot of room for contaminants. That can actually start wearing down within the cylinder liner and lead to excessive fuel blow-by, piston wash, could actually get oil up into the combustion chamber. You see where rod bearings, the tolerance is between 5 and 20, and main shaft bearings between 0.8 and 50 even. And turbocharger bearings, highly sensitive bearings that are moving at anywhere from 50,000 to 100,000 RPMs. Really tight tolerances there, and if they're really susceptible to contaminants. Piston ring bushings and valve trains and even gearing. Now, here's some studies that was done as a report came through the Society of Automotive Engineers. Give an idea of water contamination and particle contamination. Now, water contamination, you can see on the x-axis, percent bearing life remaining. Now, on the y-axis of that, you can actually see the x-axis was the water and percent water, and the y-axis is bearing life. You can actually see where, as we increase the percent of water in a bearing, how it reduces bearing life dramatically. If you look over at the right chart, it gives us an influence of the particle contamination has on the bearing life. And this is percent of the L10. I'll go into a description of that here in a minute. The L10 is the life of that 90% of a group of apparently identical bearings with a complete or exceed before the area that spalling reaches a defined 0.01 inch size criterion. But anyway, the bottom line is that we can actually see on the x-axis the filter micron rating versus the bearing life. The smaller the particles that are captured, the longer our bearing life. It's a dramatic example of actually how much contamination can have influence on bearing life. Now here's our L10 definition, just in case you want to snap that. It's defined, L10 is defined as the basic dynamic loading rating over the equivalent dynamic load rating, the exponent of equation of the life equation. Usually there's 3 for ball bearings or 10/3 for roller bearings. And here's an example of contamination control oil life cycle and the influence of water and various types of metal ions have on the oil itself. Now on the y-axis here, we have the neutralization number, the acid number, and how many milligrams of KOH, potassium hydroxide, per gram of sample it takes to bring about neutralization. So this gives us an idea of how much acid is building up in a system over time. Now this particular study, once again by the SAE, we can actually see time in hours. Here, the oil is tested up, clean and dry, and well over 1,000 hours, up to 10,000 hours, we start to see an increase in acidity. So the TAN, total acid number, it's about a 0.2. But now look at this, a 6. This is where we've actually added copper and water to the test. And see the influence it has over the neutralization number. It rises quite dramatically, quite early on, with less than 100 hours, proceeding into a really alarm limit quite quickly. So this is why actually water being one of the most common contaminants out there, we really have to mitigate that. The other thing too is that if we consider iron and copper, these ions that get in there due to wear, and sometimes also due to contamination from the outside, iron is very prevalent in dirt, these things act to catalyze the reaction as well. So we have to make sure that if we are selecting oil, we have metal deactivators in there, corrosion inhibitors as well. Moisture accelerates this oxidation dramatically, exponentially. Now, water can come in several different forms. Dissolved water in the solution, where you can't even see it, up to about 300 to 400 parts per million. The oil may actually look clean. In some types of oils, perhaps a phosphate ester, you can't even see it up to 1,000 parts per million. We can have emulsified water. That's easy to see because those are the suspended microglobules, the particles in the liquids, producing milk-like appearance. We can have entrained water. That's normally not defined in the United States. That's typically a European or Asian term, but is water suspended in petroleum or these petroleum products? Entrained water includes emulsions, does not necessarily include dissolved water though. And then we can have free water. And that's water that exists as a separate phase. Now, if I was to ask you, what do you think the most dangerous form of water contamination is? Chances are you'd probably say emulsified. But in actuality, it's not. It's free water. You see, free water can lead to emulsification. It can lead to dissolved water and entrained water, but can also lead to rust within the system as well. Now, compared to that, to emulsified, free water is the most dangerous form of water contamination. Now, here's some water-related issues. We have accelerated bacteria growth in the form of microbes. And predominantly, these little beasts require water in order to metabolize and replicate. And they will eat the hydrocarbons in an oil. We know they also do that in fuel as well. So if we have water in there, chances are we do have the opportunity for microbial growth. And sometimes folks won't consider it in a lubricated system, in a gearbox or hydraulic fluid or even turbine, but it is prevalent, especially with marine applications. Another reason to keep water out of the system. Now, once you do have microbial growth in there, it's very difficult to get it out. You'd have to completely clean and drain the entire system and basically sterilize it. Now, if you don't, you're just going to put fresh oil back in, and microbial growth will continue, and you're not going to get the infection. Sometimes people treat a biocide, and that's dangerous as well, because if you can kill those bugs quickly, you have to drain the whole system entirely. Because if you leave any biocide behind at a small percentage, as soon as it gets infected again, that'll actually jumpstart the microbial's metabolism, and they'll proliferate a lot quicker. It's a strange, bizarre phenomenon, but the same thing occurs when if you have a bacterial infection and the doctor prescribes you antibiotics. The challenge is that if you don't take the full regime of those antibiotics and you stop midway through, the bacteria do several things. One, they get smart because they replicate so fast, they can adjust. And secondly, a reduced concentration of the antibiotic actually facilitates a metabolic change in their system to make them replicate faster. And the metabolism actually works quicker. So it's a really good idea to make sure we kill completely off and keep it clean. The other thing is water can lead to loss of dispersancy, especially in engine oils, where you get the hard formation of what's called soot balls. And there is a chemical reaction that occurs with water, especially with the acidic oil additives that are found in antioxidants or even anti-wear and extreme pressure additives. These things are polar by nature, and water sure does love to grab onto these things, and they actually will take away the efficiency and effectiveness of these additives. Now, here's some typical saturation points. Motor oil, more than 2,000 parts per million, 0.2% is not good. It's going to allow the oil to become saturated. Various circulating lubricant fluids and hydraulic fluids, you see down to 300 parts per million. Beyond that, it's a really bad condemning limit. Turbine oils, they're only susceptible to varnish. It's the killer of a turbine. And then transformer oils. Now, transformer oils are not a lubricant, but it's a dielectric medium. It's an insulator, if you will. But just a little bit of water, down to 50 parts per million, can produce a conduit for electrical activity. And that can produce a short. Now, one way we obviously test for water in a system, probably most popular, is called Fisher titration. It determines a precise amount of water in there. There's a few different ways, volumetric or calorimetric, depending upon what we're looking for. The colorimetric is actually pretty sensitive, from 0.001%, there's a few parts per million, all the way up to 2%. But a much broader range we can look at with the volumetric at 0.1% all the way up to 100%. And it's an iodine water reaction through electrolysis. I wanted to show you this slide because it's a comparison of Carl Fisher versus the splatter test or spatter test. Here you take a hot plate, heat it up to about 350 degrees Fahrenheit, and put a drop of oil on there. You can actually see the percentage looking at between the spat and the Carl Fisher. Now, a technician might estimate what that percent water is just by visual, and then followed up by the Carl Fisher, and you see actually they're in pretty close agreement, surprisingly so. Give you an idea what these look like. So this is a test that can be run in the field. If you got a wet oil, or you suspect it to have a little bit of water in there, you can heat up a spoon with a torch, or maybe even I've seen some folks actually put on an engine block. I don't know if I agree with it, but you do what you do, I suppose. Anyway, they put a little bit of oil on there. If it starts to splatter, you realize you got water in there. That's not a good thing at all. Now, one contaminant a lot of folks never consider is the fact that air is in fact a contaminant. It contains oxygen, free oxygen, contains water as well. And these things can have a deleterious effect on the oil. Now, air phases, well, they could come in free, which is minimal contact on the fluid, but it can be problematic during startup. And the free is the atmosphere above the reservoir. You can have dissolved air, and some oil containing up to 10% dissolved air. And that can actually convert into entrained air with a rapid rise in temperature and pressure drop. And that's a big problem too. And actually what can occur is the oil becomes spongy. And we won't go into a lot of detail about the modulus of the oil, but it can actually, fluids aren't necessarily supposed to compress to any great degree, but when you do have dissolved or entrained air, it does allow some compression. That can create a whole host of other problems. You can also have a huge temperature increase on localized spots. Now, when you have entrained air, this causes cavitation or microdieseling, and actually a decrease in viscosity as well. Cavitation is a bit of an implosion due to pressure differential in the oil, and that actually produces shock waves in excess of millions of pounds per square inch. It could rip metal away. Now, if you ever heard one in a pump, it actually sounds like gravel's being blasted against the side of it. And then foam. That's largely cosmetic issues, and it can be accelerated by particulate contamination as well as water. And this eventually can cause cavitation as well. Now, to give an idea, here's an SAE report that was produced too. We look at different types of sectors, being the transportation, agricultural, mining, pulp and paper, forestry, power generation. And we're considering particle-induced failures versus non-particle-induced failures. Now, predominantly, abrasion is the most popular way in which you can have a particle-induced failure. And that's actually backed up by the data that we have here. You can see the transportation industry, where you have hard particles get in between the surface and start grinding away at it. You can actually produce fatigue as well. And the fatigue, that's where the particle gets in between the two moving surfaces and acts to bridge the gap. And unfortunately, the pressure is applied, and on the surface, it becomes strained and eventually cracks. The particle can move about and then become abrasive as well. But what's left behind is a surface that's been compromised mechanically, and that can lead to catastrophic failure. We see in the agriculture industry where abrasive contamination has a huge influence, as well as in mining, pulp and paper, and even in forestry. So percentage by category of particle-induced failures is 82% compared to 18% for non-particle-induced failures. Now, non-particle-induced failures, such as adhesion, that's when the two surfaces meet under extreme pressure because there's a compromise of lubricant film. And that force actually will cold weld and produce where the parts actually join. And they'll break apart under force or not. But the bottom line is it can produce more abrasive. But adhesions are a non-part of the most popular form of non-particle-induced failures as well. Now, within the study, you take a look at wear rates with different types of filtration. Now, most spin-on filters that you find in automobiles and many diesel engines, if they're not bypassed, are between 30 and 40 microns. You may get one that's a little bit better, but chances are probably not. Because they're just not built that way. The sad thing is that much study has been done, and the particles that create the most amount of wear in an engine are between 5 and 15 microns. And it makes you kind of wonder what these filters are actually grabbing, because they're not grabbing the particles that are they're producing all the failure, which is a bit of an issue. But here we can actually take a look at the performance of the crankcase filter in the x-axis versus the relative engine life. Now, relative engine life, you just give it a lifespan of 1, is achieved with a 40 micron filter. But we can actually double the life of that engine by having a filter that filters down to 30 microns, and then extend it over threefold with a 15 micron filter. But look what it does with a filter that could filter down to 5 microns. It can extend the life of that engine by 10-fold, or by 8-fold, sorry, which is quite dramatic. Now, the nice thing about this is this filter isn't just a single pass. So therefore, the beta ratio doesn't have to be that high as long as the micron rating is low, because it's going to pass through just once. If it was just a one pass through, then a beta ratio number would need to be high, greater than, say, 1,000. But because it might have to actually pass through several times, that's going to allow efficiency to build up. And those of you that have ever taken my class, you all know the efficiency equation from beta minus 1 over beta times 100. That gives us our efficiency. So we'll realize that the more passes it goes through, the more efficient it can become. Now, lots of different ways that we can actually measure these particulates. And we'll talk about these. Laser particle counters are the most popular. Many years ago, the Army had instilled a laser net finds approach. It's a very popular method for several different reasons. There's also another method called a filter patch. We'll explore that. And then microscopic particle analysis. Here's just an example of the laser. This is out of I believe this is out of the Atlanta lab. And how this works is that photon beam coming in from the laser. There's a measuring zone. We have a flow of oil coming through that are particulate in there. And as the light passes through and illuminates on a zone, it used to be where it would actually create a shadow and then it would detect a shadow behind there. But now we can actually calculate the angle of attack for scattering. It gives us a much more precise determination of particle size and population density. Now, there's a few different ways in which these particles are actually determined and defined. The ISO 4402 versus ISO 11171. It's a slight variation. What's really important is that once you do test your oil, and you are going to test it repeatedly over a period of course of time to make sure your particles aren't increasing in population or size density, you just want to make sure that you keep the same test method always. Because if you send it to different labs or they change up test methods, you're going to get different numbers. They're not going to relate the same. We can actually see over here in the 4402, the size distribution versus the NIST size distribution, which is the 11, how it's calculated. So you have an equivalent size diameter, say 13 microns versus 10. Now, in a typical particle counting oil analysis, we see the metals and contaminants and additives and physical tests. These are all the metals and the contaminants and additives. That's all in parts per million. That's achieved with the ICP. The particle count, well, that's achieved with the laser scattering. And how is this count result obtained, and what does it mean? Well, the bottom line is those numbers, the first set equates to a range of particles that are greater than or equal to 4 microns. The second, greater than or equal to 6 microns. And the third, greater than or equal to 14. Needless to say, that very first number has always got to be the largest. Now, the second number can equal the first, and the third number can equal the second and the first. But the first one always has to be the largest because that takes into account the most amount of particles that are greater than or equal to 4. Now, in the ISO 4406 chart, that number range represents the number of particles per milliliter sample. Now, as you can see, it's a range. So the very first number was a 21. That means that there's the particle size density in there greater than or equal to 4 microns, range between 10,000 to 20,000 number of particles per milliliter that are equal to or greater than 4 microns. And the second number, 19, number of particles per milliliter between 25 and 5,000. You can actually see the progression of these numbers. They double with each range number. And 16, between 320 and 460. So with each range number increase, it doubles the concentration of the particles. Now, Vickers pumps recommends a cleanliness level for various types of componentry within their systems. On the pumps, we have fixed gear all the way to variable piston. You can actually see where variable piston pumps require a lot more attention to particle mitigation as opposed to the fixed gear. Well, tolerance is a lot smaller. So particles will have a much larger influence on the overall reliability of these pumps. You can actually see in valves, though. Valves are actually quite sensitive as well. In fact, the servo valves, probably most sensitive. If you look on the servo valves, 16, 14, 11. It's a very clean system. And then 15, 13, 10, depending upon the pump pressure. We can see where the bearings actually have a requirement as well of being quite clean. Now, we have laser net fines. And in here, we have a light source. It travels through the oil sample. And the light source actually then produces shadow on the screen, if you will. And that detector picks up and relates back to an actual pixel and sends it back into the computer. And here, the pixelation is down to about 10 microns. The company that's pretty much known for this, Spectra Scientific, they've actually now produced product that'll actually get that get those pixels down even smaller. And they'll be able to adjust a little bit with certain types of algorithms to have more accuracy. It used to be where a laser net fine couldn't necessarily be used for strict particle count. I'll give you a great idea as far as what kind of particles are in there, which I'll discuss here in a moment. But for particle count, many years ago, because of the pixelation, might not have produced the most robust numbers. But now I think they've got that all sorted out. So actually, it does produce a pretty stout range for the 4406 to do particle count with. It's a powerful tool. One of the things it can do is produce an idea of what kind of wear is occurring. So if the pixels produce configuration morphology, as shown here, the system can actually determine, do those pixels are those particles related to cutting wear, sliding wear, fatigue wear, or non-metallic? Well, cutting wear, that's from pure abrasive action, where perhaps you have a contaminant entering, your filters or your breather's been compromised, and that particle is digging in and gouging out. Sliding wear, that's typically indicative of perhaps a lubricant breakdown, where we have metal-to-metal contact. Not necessarily due to a hard particle contaminant, but moreover, it can be due to a water or air contaminant, compromising lubricant film, producing more metal-to-metal contact. So whether it's cutting wear, it's where we can actually identify cutting wear as becoming the culprit due to a problem with our filtration or breather. We can say that sliding wear might be due to the fact that the oil has been compromised and the film is now producing metal-metal contact due to the lubricant breakdown, or perhaps a fluid that got in there and compromised the integrity of the film formation. Fuel, maybe different oil, perhaps water. A little bit of water can increase viscosity, but a lot of water can actually decrease the viscosity. We can have fatigue wear, and that comes about from hard particles getting between the metal surface. And then non-metallic. Non-metallic can come in the form of anything from fibers or even bacteria, or in this case, maybe even in certain cases, perhaps a different type of fluid that's not miscible. Maybe a silicone oil and globules, or could be an additive that are precipitated out, or even water in some cases. And that's the thing with particle counting. If the sample isn't prepped properly, you can actually have erroneous numbers. Trapped air, trapped water can provide erroneous numbers, thinking that you have particulate when you really don't. Now there's the filter patch. And here we're looking at the concentration of debris, and we can actually even determine the type of debris as well, whether it's abrasive, determine whether it's ferrous, non-ferrous. It's called developing a filtergram. You can also understand the ISO cleanliness code by that as well. Here's what one of the digital patch filter test setups look like. We draw a vacuum on the sample, pull it down through a micropore filter paper. And take a look at it underneath the microscope. Now, something like this, we can actually see where we determine the NASA ISO count according to the particle size. And there's a little reticle off to the side where we can actually measure it and count it by eye. Here the oil's getting a little bit dirtier. So the eye counting can actually come into 1917, 14. And here it's much dirtier, 23, 21, 18. Now here's the actual filter papers. Give you an idea what these things look like. I know the laboratory down in Perth at ALS I had witnessed where they could actually take these things and set it up in the system and actually have the system determine particle count. Much the way a computer can actually analyze the facial features of your face for identification purposes. Well, I take the same kind of software and apply it to this. So it can actually automatically count it as opposed to having human error involved. Before, if you had someone try to do this by eye, it'd probably drive them crazy because you'd be doing this all day long. But now you can actually set up the computer to do this and can actually do it automatically, which is quite effective, actually. Next steps is actually taking the size and shapes and so forth, like much the way what LaserNet finds do, and then incorporate that into the algorithm. That way, we're actually doing photography. We're able to establish perhaps the size, but also the configuration. Give us a great indication of what the potential failure mechanism is. You can identify failure before the opportunity for failure before it becomes a catastrophe. You can mitigate it and actually extend out the life of your equipment dramatically. Now here we'll talk a little bit about the microscopic particle examination process. We're actually looking at the various wear modes. You can take a look at the rubbing, cutting, spherical. And spherical is usually associated with the fatigue, where the particle actually gets in there, acts like the bridge, breaks up, and then starts rolling around, tumbling around, sliding and rolling. And for those wear modes, we can actually establish the wear types, be it scoring, cracking, spalling, laminar, or striations. And that's really taking a look at the surface as well as the surface of the particles. Give you an idea, for instance, up in the top left-hand corner where we have sliding wear. The diagnostician or an analyst can take a look at that and determine sliding wear is attributed to, obviously, we have an overloaded system, maybe bearing or gearing is being overloaded, or there's a compromise in the lubricant film. Below that is the scuffing wear, very similar. And then in the middle, we could actually have a gear wear magnification and some gear fatigue going on with just some spalling as well. Now, untrained eye, these things might be a little bit confusing, but after you start getting trained up and perhaps getting your LLA2 or your MLA3 or OMA, goes a long way to help determine what these things are and you become a diagnostician yourself. Here are some examples of some cutting wear. Cutting wear attributed to hard particles getting in there and gouging it out. Here we can actually see what it looks like on a 200 magnification, even 500 magnification, even 50. You see these long strands? How particle got in there and gouged it out. Perfect indication of cutting wear. That's attributed to hard particles getting in there, perhaps from a compromised breather, a compromised filter, or perhaps a filter that's not filtering low enough. Hard particles getting in there, perhaps from the system itself or from the outside. Now, many systems contain different types of alloys with different hardnesses. So if one particular component with a hard alloy, for some reason, that hard alloy wears, it can actually travel to another part with a softer alloy and produce a significant cutting wear. Here's what normal rubbing wear looks like. Now, in a report, I'm going to produce something like this, where we have the component details. We have the diagnostic statement, which is probably by far the most important. So our diagnostician has gone in there and assessed exactly what's going on and some action to take. Much the way a doctor would review your test results, and he or she can actually determine what the course of action, the prognosis is, and where to go from there. It actually gives you equipment status icon and so forth. So it actually also produces pitches for you. Now in here we actually can see several different things at play. Now mind you, when we start doing particle analysis, there's lots of different types of particles that we're going to find. We could find spalling, we could find fatigue, we obviously could find cutting and so forth. We could find corrosion particles from oxides. But it really determines the concentration of how many are in there as well. And that's another thing that can actually determine. Now, this is a bit of an eye chart, but actually not only does it give you historical sampling details, it also provides modes of wear. And this gives a nice little chart to give a graphical representation of the wear modes for current sample. And also what you can do is compare it on historical wear patterns to see if things are increasing or decreasing. Great way to understand the overall reliability entitlement of your system, but also how well your system's filtering out, maybe how well your breathers are working as well. Gives you historical equipment status and your analysis. Now here we have effective cleanliness, where we have target oil cleanliness levels and the ISO ratings. Now you can see how these are. Now this is a rather old chart because it just gives the XY, not the XYZ. But the bottom line is it's still indicative, obviously, that cleanliness levels, targets, and really how much longer you can actually bring your equipment down into a high reliability entitlement. In this particular oil analysis, we can actually start taking a look at the physical tests, the metals and contamination, but also the physical tests. If you look down here, we didn't spend a whole lot of time on the PQ index. That's for a later webinar, but it does give a good indication of iron-laden or ferrous-based material buildup over time without any discernible attention to size. With a PQ index, all it cares about is the fact that there's more metal being generated over time. Because with the PQ index, we're analyzing a distortion in a magnetic flux of the sample, and that's it. A lot of times, if we start putting if we put an oil through a system, and let's say we analyze it with the ICP, inductive coupled plasma, and that's the deal where we're actually looking at the parts per million for those metals. Well, that's only good for if you have up to maybe metal particles up to about 6-7 microns. Anything longer, the ICP is just not going to catch it. It's not going to burn it off. And then remember, the ICP is a system that burns that oil at a really high temperature, and it sets up those atoms to produce, of those different metals, to produce a certain color signature. It can be picked up. Now, the wavelength of the color is indicative of the metal. The intensity of the color is indicative of how much concentration is in there. That's how they do it part per million. But that oil is only in there for maybe 15, 20 seconds before it has to be evolved out. The bottom line is that if particles are much larger than, say, 6 or 7 microns, it's just not in there long enough to completely burn them out, so it doesn't pick up a pulse. So that's why the ICP, when we do elemental analysis, it's great to give a great indication of metal in the system up to particles about 6-7 microns. But anything greater than that doesn't. That's where we start to have to use other tools. PQI is a great tool to use for that as well, because we can use that in conjunction with the ICP. And if the PQ starts increasing, and it's an index over time, we know that we're generating more and more metal. Now that may or may not be picked up by the ICP due to particle size. So if, let's say, if iron remains steady, but PQI increases, we know we're generating large particles of iron or iron alloyed material. And that's still a very valuable source of information. And then if you couple that up with particle count, now you have 3 different ways to look at it. That pretty much concludes our discussion on contamination and how to test for it. We ended a few minutes early. We just want to let off and say that no system has ever failed for being too clean per se. Now, one thing I do want to clear up is that there's a little bit of misconception out there that you can filter out additives. Now that is a misconception, because you really can't filter out an additive, all right? What can happen though is your additive can be compromised due to contaminant, typically water, and it can form a rather large particle due to the fact that those additives can react with water and precipitate out. The only additive that isn't typically mixed in an oil that's dissolved is typically a siloxane-based antifoam. That's because it's a silicone oil, and it doesn't readily mix with mineral or other types of synthetics, but it does form microglobules, if you will, microemulsions. Now, if those microemulsions do get wet, they can form larger particles, if you will, or globules, and they can be filtered out. Now, if you have a detergent dispersant additive in your engine oil, and they work quite well to where actually they're grabbing onto soot or something else, they can actually be filtered out as well because they're doing their job. They're grabbing onto the soot particle, and then maybe that's big enough to be filtered out. But by and large, you can't filter out an additive. So if someone's going to tell you that their additive is going to be filtered, if a company comes in and says additives can be filtered out of a new oil, no, you can't. You just can't do it. So I did want to make sure you all knew that, and we cleared that myth up, because there's lots of myths in our business, being lubrication and tribology, and we just want to make sure we don't have our views distorted. So we are working off of science, not conjecture. Anyway, I want to thank you all for attending today during your lunchtime or pre-lunch, and we can open it up for questions right now. Feel free to give me a call anytime you want. Send me an email if you're interested in doing some more stuff, and love to be able to help you out in any way we can.
Yes, thank you, Michael. We will go ahead and open up for questions. You can use your chat box, ask a question, or even raise your hand feature, and you can ask Michael a question directly if you would like. While we give everyone a few moments, I did want to let everyone know that this webinar presentation has been recorded. All the participants of this webinar will receive a follow-up email once the recording is available to view. We also post our webinars on our ALS Global website and our YouTube channel. There you will find a wide range of video resources and past Webinar Wednesday presentations. We do have one question coming in, Michael. Matt asks, what does ICP stand for?
Good one, Matt. It stands for inductive coupled plasma, and essentially it produces one of the fourth state of matter called plasma, which is it's a high energy ionized field. In this case, we use what's called argon gas, and it makes a flame, or it's nearly not a flame, it's a plasma of about 3,000 degrees Celsius. So we're going to introduce an oil sample that's been diluted a little bit with solvent into, and atomize it into the spray, and spray it into that flame, and it's going to burn. It's going to completely obliterate that oil. But anytime we burn something, there's a release of photons. Now, I remember years ago, I'd take my son hunting, we go camping at night and so forth, and start the campfire, and go to Cabela's and pull out some of the stuff you can get in these little packets, put in the fire, it produces all different types of colored flame. And I remember the first time I did that, I was fascinated. I said, Dad, how to do that? I said, well, it's different types of metal oxides in there. And I opened up one, I showed him. You can actually see the copper oxides and the iron oxides and so forth. Well, each one of those metal oxides, as they burn, they give off a light, a specific light. Well, this works the same exact way, except here we're taking a look at the oil and the different types of metal that's actually dissolved, if not, or floating around on a microscopic basis within that oil, and we're burning the heck out of it, and that metal is going to produce a certain color. Well, the human eye can't pick that up, but this detector can in the ICP. And what it does is it determines not only the wavelength of that color that's directly related to a particular amount of the metal that we're looking at. In this case, we're looking at about 23 different types of metals, but also can understand the intensity of that flame. And that gives us a great indication of concentration. That's how we determine the part per million.
Thank you, Michael. We had another question coming in from Corey. He asks, did you say that you cannot filter out additives in oil regardless of your filter micron size?
No, you really can't. People think they can. Listen, you're not going to get a filter down below 2 microns. If you had a micro sieve or something like that, a molecular sieve, and you had it ionized, there's a way you could probably do it, but nobody does that. Nobody would do that. So the typical filters anybody can ever buy out there, if you get a 1 micron absolute filter, you're not going to filter out a quality oil. There's some blend that might not actually blend siloxanes antifoams to the point they're below a micron in size. That's not the case for good oil companies there. They blend it appropriately. The only time you could ever filter out an additive is if that additive's been compromised. And the additives that typically become compromised are antifoams, because they do get wet. They do form larger emulsion particles, and they can be filtered out. But a brand new oil, you can't filter out the additives. And I challenge anybody on earth to prove me wrong, because I've been schooled on it myself, because I used to believe that many years ago until I was schooled on it. Once you're schooled once, you don't have to be schooled again. But now you really can't filter out. You can't. No one ever had a failed system due to high cleanliness, and filtration works. The challenge is that you don't want to filter out, or you do want to filter out things that are hurting you, but the water is what's making these things precipitate out, and sometimes other additives. If you have dissimilar oils added where they have a interaction between the two additives, then you can have a bit of a problem. But that's precipitating on it. That's not the filter's problem. That's the fact that you put the wrong oil on top of the new one. So now you can't filter it out.
Thank you, Michael. We had another question coming in. It was in Spanish, so I just had it translated. One of the questions says, how does tribology apply to contamination control?
Well, that's a good question. And tribology is really, it's the science of friction, wear, and lubrication. And Peter Jost had coined that many years ago. The root comes from tribology. It means tribo is to rub or to wear in Latin or Greek. I don't forget it, some ancient language. And ology is the study thereof. We can actually take a look at what's in our oil on a microscopic basis. It gives us an understanding of where it's coming from. If we understand the genesis of these particulates and these contaminants, we can do something about getting rid of them or not allowing them in the system to begin with. If we see that a system contains a certain concentration of water or fuel or whatever, we realize that it's coming from the outside typically, or the internal mechanisms. If we're seeing that the particles perhaps are from the outside or generated internally, that's an indication of what's going on with our systems as well. Either our filtration's been compromised, our breathers might be compromised, or for that matter, the lubricant itself is compromised and it's allowing surface-to-surface contact. So tribology gives a perfect understanding of the contamination, the performance, their overall wear condition, and the contaminant, I've said, in the oil condition.
That question was from Roger. He has an additional question. What is the correct procedure to sample or display the grease or oil?
Well, for sampling grease, I always refer MRG Labs as a grease thief, and they're excellent at it. And I know ALS works closely with MRG Labs too, and there's the whole procedure for properly taking a sample of grease. As far as oil goes, we had a webinar on that as well. You always have to consider this. If you're pulling a sample, the most important part of sampling, obviously we're going to say cleanliness, but actually I'm going to divert away from cleanliness. I'm going to say sample information. If you don't put the right information on your sample ticket, and a lot of information for that matter, it doesn't matter if the sample's clean or dirty. It's useless to you and the lab. So sampling, the information sample identification form, is essentially, there's nothing more important than that. But secondly, how you pull a sample. When you're pulling in from a dirty system, expect that your sample is going to be dirty. And it's going to be dirty not only from maybe what's going on within the oil, but also how you took the sample to begin with. My recommendation is, if you're going to have to pull it out in the field, try to be as careful as possible as not to do it in a windy day where you're starting to maybe, if you are testing maybe a hydraulic system for particulate count, protect as much as you can. The other thing is that there's a pretty cool trick. If you take your sample bottle, don't open it up, keep the cap on, stick it in a clean Ziploc baggie and seal it up. And then you can actually unscrew the cap while it's still in that Ziploc bag, okay? And then you can actually poke, whether you're taking it from a mini-mess, which is an inline oil sample, or from the vacuum pump, and actually poke that right through the plastic going right into the jar. That way the jar is still in the bag, and the only thing, it's not really going to be compromised with particulate. Making sure you're always using a clean tube and a clean mini-mess or whatever, clean valve probe. Flushing out any dead leg sample from the sample jar as it's coming out of the system, and then taking a representative sample that's hot, not too hot. Obviously, wear your protective equipment, gloves, eyeglasses, all that stuff. But take it after that oil has been circulated for a little while, like 15 to 20 minutes. Great if it's running. Got to make sure you're safe. Don't take a system if it's going to make an unsafe environment. but make sure it's hot and then pull that out. And then after you've drawn that sample, get rid of that tubing or clean out the mini-mess valve probe. And then while the sample bottle is full with your oil sample with the cap off to the side, still in the Ziploc sealed bag, by the way, you take off the valve, you take it off the cover. The only thing now is a small little hole that's in the Ziploc bag. And then you take it and move over that cap onto the top, screw it tight. And then you can just keep it in the bag as well. Make sure that it's labeled up appropriately, send it to the lab. Pretty straightforward stuff. Make sure that you're looking at all opportunities for failure when it comes to contaminant entry that isn't coming from the system. That's the best course of action. We have a nice little video on that as well. If you go into the ALS Tribology website, there's a great instructional video on how to do it. It's pretty straightforward.
Also, we did get a question from Matt. He does ask, are the previous webinars archived and available somewhere? Yes, we do host all of those on our ALS Global website. You can just go to alsglobal.com, and then in the search bar, you can search Webinar Wednesday, and there you will find all of our past Webinar Wednesday presentations. We also have all of our other video resources are all posted on our YouTube channel, which is under ALS Limited, and you can search that within youtube.com.
The other thing too, Kelly, I want to make mention of is that ALS Atlanta, the Atlanta lab, it will be hosting my MLT/MLA certification preparation class on December 2nd through December 6th. Now, it's a 4-day class. It's intense, but it's probably one of the best classes you can ever take in your life when it comes to becoming certified with your MLT/MLA. Not many classes out there will do this. Now, it is a 4-day intense class, but here's the deal. You will be prepared to take on Friday both those exams, and our pass rate is exceptionally high. It's probably, if you come out and take that exam, take that class, it'd probably be one of the best classes you've ever taken in your life when it comes to pretty much anything. And I'm almost going to guarantee that. I won't give you a money back guarantee, but I'll give you a gentleman's handshake to make sure that you're going to have one hell of an experience. The bottom line is that's going to be in Atlanta, December 2nd through the 6th. We're also going to have one in Houston the beginning of February as well. Those things are available online. You can enroll as well. I definitely, those who want to get more in touch with the whole world of lubrication and oil analysis and so forth, the MLT really focuses on lubrication technology and how to the storage and management and application of lubricants for real life applications. It's not all this theoretical stuff that some other things explore. And the MLA goes into a lot of detail on oil analysis and diagnostics. Well, this course explores both these bodies of knowledge and does prepare you for taking both exams on that Friday. So please, if you're interested, definitely access the site, get a hold of Kelly, whatever it is, and love to be able to see you there in Atlanta. We still have a few more slots open. So.
Yes, we do. And the additional question says, what are the recommendations for controlling contamination in oil and grease?
Well, one thing has to do with application. You know, and actually even before that, in application, we come in, one thing has to be considered during the whole application process is the cleanliness of the product coming in. Now, there are companies out there that will filter their oils and even their greases down to where they're very clean. And there's other companies that don't, but the bottom line is as soon as you get into your shop, make sure that your storage facilities are internal. External storage facilities, you're just going to add problems. You spend a lot of money on this oils and these greases, make sure that you have some sort of place inside that's got temperature control and isn't dirty or wet to where you are going to store your fluids. And when you do use them, I highly recommend using a filter cart to put those in the system, be it a hydraulic fluid or even gear oils or engine oils or anything for that matter. You can't necessarily use oils. And also, I would always recommend if you are dealing with the circulating system, go with the lower micron rating, but not necessarily it's important. But if it's circulated, something like that, in that case, you might want to think about a lower micron filter with maybe a low, okay, and that help you out. And the other thing too is that sometimes you might want to bring somebody, a consultant from the outside, to have them assess how clean your systems are. You know, fresh eyes are usually the indication of what's going on. A lot of times an assistant may not understand how filthy you are. Bring me where do you think it's coming from on my water, my chemical? And that's probably good. Storage applications. When you deal with grease, dirty grease guns, dirty jerk fittings are horrible. You can get grease fittings that have covers on them. I'd recommend that. Breathers, you can never go wrong with a great breather with a desiccant filter. You can never go wrong. And also, anytime we're adding oil in, you want to make sure that it's a closed system and it's pumped in to where you're not doing an open pour. If you're able to look at all those different ways to try to eliminate as much contaminants as possible, you will eliminate contamination. But it requires a really concerted effort to try to first identify where it's coming from and then set up some protocols with some standard operating procedures in order to take care of that. And then obviously monitor to make sure the changes you are making make sense and are having some sort of positive influence. And lastly, if I could suggest, incorporate your key performance indices on these. If you don't know how to set up a KPI, there's my phone number, there's my email. I'd love to do it for you for free. I don't mind, we'll help you out any way we can. Every organization should have a KPIs in place, all right? So that's something to definitely consider, key performance indices. And these are typically ways to measure, how you're going to measure it over a particular segment of time, and what your overall goal is, and what your values are getting to where that goal is.
But I just wanted to remind everyone that we do record this webinar presentation, and you will be receiving an email sometime next week with this presentation, so you can go ahead and rewatch as needed. Again, thank you, Michael, for presenting today, and thank you to everyone on this call for attending, and enjoy the rest of your week.
Great, thank you very much.